Okay, last night I showed you how to find the direction of an electric field from a collection of charges, and today I will show you how to figure out the actual magnitude of the electric field, so the field strength from a collection of charges. First, I want you to think about the fact there are two ways to find the force on a charged particle. One is if there is a field present, F equals QE, and another one is if there is simply one other charge present, K, Q1, Q2 over D squared. Well, maybe I could use the fact that these are both equal to the electric force on a charge to figure out what the field created by one charge could be. So let's say I wanted to know the field created by Q1. Well, in that case I could say, wouldn't I put Q2 in the electric field created by Q1? So we could say if we had the electric field created by Q1, we would put Q2 in it. And from that, we could then set the two equations equal to each other. So now we have Q2 times the electric field from Q1 equals K Q1 Q2 over D squared. And if this is, in fact, the same Q, those two sides cancel, and the electric field from Q1 is K Q1 over the distance from Q1, wherever you're trying to measure the electric field. So this is, in fact, the formula that you use when you're finding the electric field from a charge. Now I'll make up a problem. Let's say we have a charge Q of 1 nano, that's micro, I already wrote it, 1 microcoulomb. And I want to know what is the electric field strength from that charge when I am at a distance of 1 millimeter. Okay, so I'm looking for the electric field strength from this charge with 1 microcoulomb when I'm at a distance of 1 millimeter. So we just wrote that electric field strength is kq over the distance squared. So in this case that would be 9 times 10 to the 9th Newton meters squared per coulomb squared times 1 times 10 to the negative 6 coulombs divided by 1 times 10 to the negative 3rd meters squared. And now we find what the electric field strength at that point would be. And I find that the electric field strength at a distance of 1 millimeter would be 6 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 newtons per coulomb. I think what might be surprising to you is that the distance from the charge does in fact matter when calculating the strength of the electric field, because I've only showed you so far fields that were uniform. The field lines were all the same closeness together when you put a charge in them, and you just knew what the strength of that electric field was. And we said it was the same everywhere. But if you're looking at a point charge, so just say one positive or negative, then notice the field lines get farther apart the farther away you get from the charge. They're really close together, close to it, but kind of far apart, far away. Close when you're near it, far apart, far away. And so the field is getting weaker the farther away you go from that charge, which is why there has to be that distance part when you're finding the electric field strength from a point charge. Alright, now let's try this example. Two charges are separated by 5 centimeters. Find the magnitude and direction of the electric field at point P, which is 1 centimeter to the right of the negative charge. So this right here is 1 centimeter. Okay, so I need to know the direction and field strength from each charge. The direction part should be easy. It's what we focused on yesterday. So over here at this point, point P, from the red charge, since field lines point away from positive charges, we should have a arrow pointing to the right. And since that blue charge is closer, there should be a bigger arrow pointing toward the blue charge because a positive would want to move toward the blue charge. So overall, my estimation would be that the direction of the field is going to be to the left. However, it could turn out that that red charge is so strong compared to the blue charge that maybe it does overpower it despite the distance. However, we can check, but for now, it looks like the direction will be to the left. Basically, I'll set these up like their net force. I know which direction each one points. I'll calculate the field strength and call one direction positive, one direction negative, and see what's left over at the end. For the red charge, let's do that. Its electric field, the equation we just looked at, kq over distance squared. So at point P, we're now 6 total centimeters away, so our distance would be 6 centimeters. We've got 9 times 10 to the 9th Newton meters squared per Coulomb squared. And it's 9 microcoulombs, so 9 times 10 to the negative 6 coulombs. And 6 centimeters, for those keeping score at home, that'd be 6 times 10 to the negative 2 meters. Calculate that field strength. But that distance must be squared, don't forget about that. When I do that, I get that the electric field strength from the red charge is 2.25 times 10 to the 7th newtons per coulomb. And that is to the right. As we said earlier, the red charge has its field pointing to the right because field lines go away from positives. Now from the blue charge, electric field strength is kq over the distance squared, and that would be 9 times 10 to the 9th Newton meters squared per Coulomb squared times negative 4 10 to the negative 6 coulombs, microcoulombs. That's only 1 centimeter away from the place we're talking about. So 1 times 10 to the negative 2 meters squared. Alright, when I calculate this, I'm going to go ahead and drop the negative. And the reason for doing that is I'm taking care of the directions with vector addition. So right now I'm just figuring out the magnitudes or the strength, the number, and I'm going to take care of the direction using vector addition, my red and blue vectors that I've drawn. And so I won't need to know the direction coming out of the math. I'm using the visual to get that, and a negative or positive here would basically be telling me the direction, but I'm doing that once again visually just by adding the two vectors together. So when I carry out this calculation, I get 3.6 times 10 to the 8th newtons per coulomb, which is clearly bigger. So we were right, the blue vector is bigger, meaning our field is going to end up being to the left. Since these vectors are pointing in exactly the opposite direction according to my drawing, I will subtract these two amounts. So that would be the blue vector minus the red. So 3.6 times 10 to the 8th minus 2.25 times 10 to the 7th. 3.6 times 10 to the 8th newtons per coulomb minus 2.25 times 10 to the 7th newtons per coulomb. And I get the resultant electric field is 3.3, I'm going to round here, 8 times 10 to the 8th newtons per coulomb. And we know it is to the left because the blue vector was bigger, so when you add the blue and red vector, blue one's bigger, you got some left over to the left. Alright, one more example. Find the magnitude and direction of the electric field at point Z at the square's center. Okay, so 4 charges that I'm going to have to add together. Now that vector addition can get a little messy, so let me talk you through a strategy for keeping it simple. First, I'm going to assign each a color. Let's call this one the purple one. This one the kind of, I guess that's teal. This one the orange one. And I'm actually going to avoid exact red and blue because the charges on the screen are already red and blue. This one over here, the green one. So I'm first going to look at the field direction from each one. First, the purple one. At point Z, since all the field lines from the purple charge will point away from it, since it is a positive charge, then at point Z, that purple vector would point away. All right, looking at the teal one, at point Z, that vector would also point away from the teal one. So notice I'm just kind of making an imaginary line from the corner to the center. That's how I'm deciding where to put my vectors. From the green, that one will also point away, so following that same strategy, that away. Now field lines will point toward the orange one down here in the corner since it's negative. So we'll also have, I shouldn't have made that one so sloppy. We'll also have an orange vector down this way. The reason I did that is because now I notice that I could easily add the green and purple vectors since they are in fact forming a straight line with each other. I'm going to add the green and purples, and then once I've done that, I will then use vector addition to add those two to the teal and orange vectors. Now I do know they're pointing in exact opposite directions because these charges are at the corner of the square. If I were to have a charge not in this corner, that would mess up these symmetries. And so if this green one were moved, say, up to here, it would not then have a field line in the exact opposite direction of the purple one in the other corner. Not the CST, this is AP. The AP exam is nice to you in AP Physics B. If you were to take the calculus-based version of AP Physics, AP Physics C, you would have to do a lot more complicated configurations. But since you're in AP Physics B, this right here is as complicated as it gets, and I'm showing you the tricks of using kind of the symmetries of these shapes. If you know these two, the purple and the green, are exact opposite corners, their vectors will either point exactly in the same direction, in the case of the orange and the teal, or they will point in exactly the opposite directions, in the case of the green and the purple. You might then think to yourself, well, can't we just say the green and the purple cancel out? That would only be true if the green and purple charges were of the same amount. And looky, we did turn out to be lucky. They're both positive 3 microcoulombs, and since they are the same size, both exactly the same distance from the point we're talking about, if we look at our equation, E equals kq over d squared, they'd have the same q, the same d squared. K is just a constant, so they'd both be the same. And since they're pointing in opposite directions, they will in fact cancel each other out. So those two, we get to ignore. They cancel each other's field out. And now we're just to the last two. And so this won't be too hard. We'll only have to add 2 things together. However, we do still have to carry out the calculations for each, the teal and the orange. So starting with the teal charge, our electric field strength is kq over d squared. And if I fill in that info, 9 times 10 to the 9th newtons meters squared per coulomb squared. The teal charge is 3 times 10 to the negative 6th coulombs. Okay, so this distance is going to be a bit tricky. Notice that it's not 2 centimeters away. In fact, that shape right there is a diagonal and suggests to me we're going to end up using the Pythagorean theorem. So we got to figure out how far away the teal charge is from point Z. I can create a little triangle right here out of the lengths of these sides. Notice that this side of the triangle will be the same size as this length here. And if Z is in fact at the center of the square as the problem says, the length of this side would be 1 centimeter, half of that 2. the length of this side would be 1 centimeter, meaning the length of this side of the triangle down here is also 1 centimeter. Now I can figure out the total distance to point Z using the Pythagorean theorem, because the distance would be the hypotenuse of that triangle. So C squared equals 1 centimeter squared plus 1 centimeter squared. 1 squared is 1, and so we get C squared equals 2 centimeters squared. If we take the square root of that, we'll get C equals square root of 2 centimeters. Okay, so that is the distance here. So if I bring that back up to what I was originally writing, all over square root of 2 centimeters squared. And now I carry out that math. But notice something that I've got to do first. I've got to take the square root of 2 centimeters and turn it into meters. So right now that's in centimeters. So the square root of 2 is in fact just a number. If I grab my handy dandy calculator, it says the square root of 2 is about square root of 2, 1.414. So that's centimeters. Changing that into meters, 1, 2 to the left, I get 0.01414 meters, and I can put that back in as my distance. I was going to try to divide this side up so I could get both on here, but I think I should just give up on that, and I'm going to rewrite this equation because this is getting sloppy now. So E is 9 times 10 to the 9th Newton meters squared per Coulomb squared times 3 times 10 to the negative 6 coulombs, all over what we just found out, 0.01414 meters squared. And if I do that math now, I get the electric field strength is 1.35 times 10 to the 8th newtons per coulomb. And now for the orange charge. Alright, create a little more space here. The orange charge, E, equals KQ over the distance squared, which would be 9 times 10 to the 9th Newton meters squared per Coulomb squared, times 2 microcoulombs, and that's negative. Remember I said we're handling the directions manually by looking at what way the vectors point, so I'm just going to write that as 2 times 10 to the negative 6 coulombs divided by. Now, since this is a square, what's nice is that the distance from this charge to the center would be the same as from any of the other corners. So we can just reuse our earlier math, 0.01414 meters squared. Carry out that math. I'm going to round again. I get that this one is about 9 times 10 to the 1, 2, 3, 4, 5, 6, 7th newtons per coulomb. So that's the orange charge. Notice from our drawing that those two charges we decided point in the same direction, which means we would just add the vectors together. We would subtract if they pointed in the opposite direction. So our total two electric fields together, the teal and the orange, should be, this is E, would be 1.35 times 10 to the 8th newtons per coulomb plus 9 times 10 to the 7th newtons per coulomb. Just adding those two together. I get that that total is 2.25 times 10 to the 8th newtons per coulomb. And if we look back at that tiny drawing, it's gotten kind of small, but both vectors were down to the left, so total, they would still be down to the left, just a bigger vector, with a direction of down and to the left. So that is our final answer. Our problem did ask us for direction, so not including direction would make it wrong. And plus, I called this a vector, gave it the little hat. So I had to include direction just because I called it a vector. That's it. This has been a long video, but a lot of useful stuff in it. See you tomorrow.